Today we're looking at linear and quadratic approximation, our learning objectives to get a better understanding of linear approximation, quadratic approximation, the Hessian matrix, and then we should be able to calculate linear and quadratic approximations and calculate the Hessian. Cool. If we first just look at single variable linear and quadratic approximation, if we just have a function with just one variable, then to linearly approximate that function, we would use this formula. And for a quadratic approximation, we would simply just use this formula. And this is just from the Taylor series or Taylor expansion. Now, what we need to know is linear approximation for multivariable functions. So if we have a function with two variables x and y near some point x0, y0, then to linearly approximate that, we sub in our point into the function, then we partially differentiate that function with respect to x, and we partially differentiate that function with respect to y, and then we do x minus this value, and then over here we are doing y minus this value, and that would give us our linear approximation. Just as vector notation, we've got the vector x, which is just x, y, so we're substituting this vector into here, so that is just x0, y0. Then over here we've got the gradient vector, which is just partial derivatives, and we are substituting in this vector, which is over here, into these partial derivatives, and we're multiplying that by the vector xy minus x0 and y0. Cool. So this exact same thing represented in a vector form. If we now look at the Hessian matrix is just the matrix of all the second order partial derivatives. So we've differentiated partially with respect to x twice. Over here, we've partially differentiated with respect to x and y. Over here, we've partially differentiated with respect to y and x. And over here, we've partially differentiated twice with respect to y. Some facts about the Hessian is that the Hessian is always symmetric. That is because these two will always or should always be equal to each other. The Hessian allows us to see the curvature of the function, and the Hessian is just the multivariable equivalent of the second derivative, so f double dash of x, in single variable calculus. Just to quickly talk about what we mean by curvature. Curvature is just simply describing how quickly the slope of a function is changing at a given point. So if there is no curvature, it just means that the slope never changes. So the curvature is 0. And this is why the Hessian of a linear function is always 0, because the function is just a straight line. If it's a positive curvature, then it just means the function is bending upwards and the slope is increasing as you move along the function. So this would be a convex function. And then if we have a negative curvature, the function is bending downwards, like some sort of hill, the slope is decreasing, and this would correspond to some sort of concave function. Cool. Now, the Hessian links to quadratic approximation. That is because the formula to find the quadratic approximation of a function, which is two variables x and y, near some point x0 and y0 is this. So just like before, we are subbing in this point into the function. And then what we're doing is we're finding out the gradient of this function, which is just partial derivatives with respect to x and y. And we're subbing in this point into here, this T just stands for transpose. So we're going to write the vector as a column vector like this. And then we've got this, which is delta x, which just represents, should be delta of the vector x, which is just x minus x naught, and then y minus y naught. So exactly what we saw before. So up until this point, that is just the same as the linear approximation formula. Now, if we have a look at this, we've got a half delta xt and then the Hessian, and we are substituting in this point into the Hessian and then delta x. So if I write this out in its full form, we have got delta x, which is just x minus x naught, and then y minus y naught. The Hessian matrix substituted with the point substituted in it, and our Hessian matrix was just the second order partial derivatives. So this, and then once again, our vector delta x. And of course, this is transposed. So this is essentially what the quadratic approximation of a function with two variables will look like. This half just comes from over here. So if we look at the Taylor expansion, this, if we ignore this, this is actually over 2 factorial, and 2 factorial is just 2, so hence why we get that a half. Cool. Hopefully this formula makes sense to you, but we will look at some questions and you can familiarize yourself with it then. Just a quick little fact about the quadratic approximation formula. It just adds a second correction on top of this linear correction, as you can see, using the Hessian. And what that means is that our approximation is just a bit more precise because we're now modeling the function with a higher power instead of looking at it in a linear way. Cool. If we look at this function, which is a function of x and y, which is equal to x to the power of 0.5 and y to the power of 0.5, and we're going to be approximating this function near the point 4, 4, and it's going to be a linear approximation. So if we correctly recall the formula, it's going to be substituting in this point, then the plus partial derivative of this function with respect to x, which is multiplied to x minus 4, and then plus partial derivative with respect to y, and that is being multiplied by y minus 4. So now if we substitute x is equal to 4 and y is equal to 4 into this function, we get 4, and then plus over here, if we work out the partial derivatives, we get these as the partial derivatives. Substituting in 4, 4 into here, we get a half. And then if we do the same thing, substituting 4 into the partial derivative with respect to y, we will get a half and y minus 4. If we now expand the brackets, we just get half x plus a half y as a linear approximation. Cool. Moving on to our next example, we are now going to be looking at a quadratic approximation, and we're going to be approximating the function x squared plus xy plus y squared near the point 1, 1. So once again, if we recall what the formula is, this was the formula. So if we first begin by working out the partial derivatives. So partially differentiating this function with respect to x, we get 2x plus y, and differentiating it partially with respect to y, we get x plus 2y. Now, to work out the second derivatives, we will partially differentiate this function with respect to x again, and so we get just 2. And then if we differentiate this function with respect to y, we get just 1. Again, if we now differentiate this function with respect to y again, we just get 2. And if we differentiate it with respect to x, we just get 1. So our Hessian becomes 2, 1, 1, 2. And this is a symmetric matrix. And then our gradient of the function is just 2x plus y, comma, x plus 2y. Now, from this information, if we calculate the quadratic approximation, we will first begin by substituting in 1, 1 into this function, because that's what we need to do first. So we get 1 plus 1 plus 1, which is 3, and then plus the gradient with 1, 1 substituted in, just gives us 3 and then 3. And we're going to multiply that with x minus 1 and then y minus 1. And then this is going to be plus by a half x minus 1, comma, y minus 1, brackets the Hessian, which is 2, 1, 1, 2, and then x minus 1, y minus 1. If we now expand everything out, 3x minus 3 plus 3y minus 3. So that's just me doing the dot product between these two vectors, plus a half x minus 1, comma, y minus 1, brackets. If we first multiply these two matrices, we get 2x minus 2 plus y minus 1, and then x minus 1 plus 2y minus 2. If we just continue on with this, we can see that these are going to cancel, and we get 3x plus 3y minus 3 plus a half, brackets. If we just simplify this, we get x minus 1, comma, y minus 1. So that's just me rewriting this. And in brackets, 2x plus y minus 3. And then x plus 2y minus 3. So now, if we multiply these two together, we get x minus y, brackets, 2x plus y minus 3 plus y minus 1, x plus 2y minus 3. If I now expand everything out, we get 2x squared plus xy minus 3x minus 2x minus y plus 3. And then over here we've got plus xy plus 2y squared minus 3y minus x minus 2y plus 3. So we get 2x squared plus 2y squared plus 2xy minus 6x minus 6y plus 6. And expanding the half out, we get x squared plus y squared plus xy minus 3x minus 3y plus 3. So this and this cancel, this and this cancel, this and this cancel. So we're just left behind with x squared plus y squared plus xy. Cool. Pretty funny how the approximation is just the exact equation. So yeah, all that means is just the quadratic approximation is perfectly exact with 0 error. So I guess it isn't really an approximation. So I guess it isn't really an approximation. Cool. If we do the same thing with this question, so this is just our formula, and if we sub in 1, 2 into our function, we get 17. If we now work out the partial derivatives, we get 2x, and then for y, we get 6y squared. And so we get 2 brackets x minus 1 plus 24 brackets y minus 2 plus a half x minus y, y minus y transposed. The Hessian, which is just going to be 2, 0, 0, and then 12y. And then x minus y, y minus y. If we substitute 2 as y, we just get 24 over here. So this is 24. So if we now expand everything out, we get 17 plus 2x minus 2 plus 24y minus 48 plus a half, and then brackets x minus 1, y minus 1 transposed. And over here, we just get 2 brackets x minus 1, and then 24 brackets y minus 1. And I'm actually just going to keep it in this form. So 17 plus 2 brackets x minus 1, and plus 24 y minus 2 plus a half brackets 2x minus 1 all squared plus 24 brackets y minus 1 all squared. And so we get 17 plus 2x minus 1 plus 24y minus 2 plus x minus 1 all squared plus 12y minus 1 squared. Hopefully that makes sense. Also, just realised that these should just be 2's because our y0 over here is 2. Hopefully you spotted that before me. Cool. If we now have a look at this multi-part question, which is something we may see in the exam, we have a firm's production function, which is given by a function which has variables k and l, and is equal to k to the power of 0.5 and l to the power of 0.5, so a Cobb-Douglas function, and the firm is currently operating at the point 4, 9. Find the gradient vector of the production function is what that should say, and evaluate it at the point 4, 9. So the gradient of our function, we have done this many a time now, which is 0.5 k minus 0.5 l to the power of 0.5, comma 0.5 k to the power of 0.5, and then l to the power of minus 0.5. And if we sub in 4, 9, we get 3 over 4 over here, and then 1 over 3 over here. Bobby is now telling us to write down the linear approximation near the point 4, 9. So the function k and l, if we just write down a general formula first, we will have to substitute in our two values, which is 4, 9, and this plus our gradient, where we have substituted in the points k0 and l0, which is again 4, 9, and we need to multiply this by k minus k0 and then l minus l0. Cool. If we start doing this, we get 6 plus 3 over 4 and then 1/3 multiplied by k minus 4 l minus 9. And so we get 6 plus 3 over 4 k minus 4 plus 1 over 3 l minus 9. If we now look at part C is telling us to calculate the Hessian matrix and evaluate it at the point 4, 9. So to evaluate the Hessian, we're just going to differentiate this again with respect to k. So we get minus 1 over 4k minus 1.5 L to the power of 0.5, and then minus 1 over 4k to the power of minus 0.5 L to the power of 0.5, so minus 0.5, and then over here minus 1 over 4k to the power of minus 0.5 L to the power of minus 0.5, and then over here minus 1 over 4 k to the power of 0.5 L to the power of minus 1.5. If we now substitute in 4,9 into our Hessian, get minus 3 over 32 here, and minus 1 over 54 over here, and minus 1 over 24, and minus 1 over 24. So, moving on to part D, if we write down the full quadratic approximation, we already have the linear approximation, which was 6 plus 3 over 4 k minus 4 plus 1 over 3 L minus 9. And all we need to do now is just sandwich the Hessian between the vector k minus 4 L minus 9, which is transposed, and our Hessian, and then again k minus 4 L minus 9. And I think I'm just going to leave it in this form, as it might get too messy if I start expand this out. Also, just a mistake of mine. This should both be pluses, because we're not timesing by negative 0.5. So yeah, again, these should both be pluses as well. Cool. Moving on to just part E, which is telling us to find the eigenvalues of the Hessian. For that, we will have to do trace of the matrix, and plus the determinant of the matrix, which is H. Using it as around, this will give us the quadratic characteristic equation. So the trace of the matrix is just adding up the elements in the diagonal, which gives us 97 over 864, plus the determinant of the matrix, which is just 0. So we get lambda is equal to 0, and lambda is equal to minus 97 over 864, apparently. So yeah, that is that question. Hopefully that all made sense to you. Thank you very much for watching, and do use the link in the description to buy me a coffee. Thank you very much.